Hello. In this video, I will show my 16-bit Minecraft processor in operation. I walked through this design in another video, which I will link in the description. Much of this video will be fast forward as the processor is very slow. I built 64 memory locations as I do not need more and it would be too large to implement more. The first 32 addresses are read-only memory. This makes it easier to program as I just have to flip levels. The remaining memory addresses are capable of both reading and being written to. The processor is currently programmed to add up three numbers in a loop. It should add 5 plus 6 plus 7 to get to 18. First, the processor adds the value stored in register 7 with the number 9, and then loads the data at that address into register 0. This should set register 0 to the value 2. Next, the processor adds the value in register 7 with the number 10, and then loads the value at the corresponding address into register 1. This should set register 1 equal to 5. Next, the processor adds the value in register 7 with the number 11 and loads the value at the corresponding address into register 2. This will set register 2 equal to either 6 or 7 depending on which iteration the loop is on. Next, the values of registers 1 and 2 are added together and the result is stored in register 1. Next, the value 1 is added to the contents of register 7, and the result is stored in register 7. This increments which memory is loaded. Next, -1 is added to the value in register 0, decrementing the counter. Next, the program checks if the value in register 0 is positive. If it is, the program branches back to the third instruction. If not, it continues on. Next, the result of the addition stored in R1 is then stored in the memory address corresponding with the value of R3. Finally, the program will enter an infinite loop, halting all actions. The remaining 4 addresses correspond to the numbers 2, 5, 6, and 7. Register 3 stores the number 32 after a reset. This allows the data to be stored in memory location 32 very easily, which is useful since it's the first writable location. It is currently set to 0 as nothing is stored in it. This switch handles the reset of all the registers, so when I flip this off, the program will start. This switch enables the clock. It was primarily for debugging. As I did not do a good job playing this design before I started building, the clock needs to be very long, so I will fast forward a lot of the execution so this video is not an hour long. These lamps correspond to the state of a finite state machine that controls the operation of the processor. States 0000, 0001, and 0010 correspond to instruction fetch. State 0000 loads the memory address register with the contents of the program counter and then increments the program counter. State 0001 loads the instruction from memory into the memory data register. State 0010 loads the instruction into the instruction register. The next state, state 0011, is the decode phase. The finite state machine determines the next steps to take. These 4 states will occur for each instruction, then other states will occur that are specific to the instructions. State 1000 is the first state in the load instruction. The address is calculated and then loaded into the memory address register. These red wires are enable signals for memory addresses. Next, the address is sent from the memory address register to the decoder. You can see it updating. The enable signal for the data is now activated, and the data is loaded into the memory data register. The state is 1001. The MDR then outputs to the central bus, which sends the signal to the register file, which then overwrites the destination register. The state is 1010. The next instruction is loaded and the process repeats as the first three instructions are loads. The MAR updates, the address is selected and then evaluated. The instruction is loaded into instruction register and then evaluated. Eventually, it reaches the first add instruction. This has the state 0100. Since the first addition is between two registers, the values from each register will go through these large multiplexers. This selects which signal to use. There are 32 8-to-1 muxes, as there needs to be two outputs from the register file. The lime green is the primary output and the blue is the secondary output. These signals then reach the arithmetic logic unit. This mux selects between using immediate values from the instruction and the secondary register output. Once the add instruction is done, it fetches another instruction. For this next add, it uses a sign extended immediate value from the instruction, the yellow wool lines. In this case, it passes the value 1. The state is identical to the previous add where two registers were combined. A value from the instruction signals whether it should use immediate or not. The output is again sent to the bus and stored. For the third add, again an immediate value is used, this time -1. Since this is 2's complement numbering, all bits being 1 is -1. This ends up resulting in the number 1 being stored to the register. The next instruction is then selected. This is a branch instruction which can modify the flow through all the instructions. This segment stores if the output from the previous instruction that wrote to the register file was positive, negative, or 0. This can then be used to modify the control flow of the program. The branch instruction determines which to check for. In this case, it looks for if the previous value was positive. The branch instructions evaluate in the decoding phase. You can see that the gray wool line is on. This signals that the branch condition was met. Now the PCMux, instead of using the PC plus 1, will use the PC plus offset. This will result in the PC going back to the third instruction. This time around, the last number is loaded. The data is sent on the bus to the registers where it is stored, and the add instruction is loaded. The data from registers 1 and 2 are added and the result is passed through the bus. Now register 7 is incremented again. Next, the counter value in register 0 is decremented. Since it was 1, it becomes 0. This is sent back to the register file, as well as causing the state bits to update. Since the value is 0, the 0 bit is now on. Since the branch is not looking for 0, the PC updates as usual, and so the program goes to the next instruction. Now the store instruction is accessed. The data is passed through the ALU and then goes to the bus and into the MDR. The pink wool comes out of the bus and goes to the MDR. On the next clock cycle, this will be sent to the memory write line. The data is then written to the selected memory address. One final instruction must occur so the processor does not do random operations based on the numerical values instead of actual instructions. The halt instruction is loaded. This instruction traps the processor in state 0, 1, 1, 1. It will remain in this state until the system is reset, ensuring that the processor does not execute any unintended operations. As you can see, the result was correct, as the output is binary 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, which is of course 18. And so therefore the processor worked properly.